Wait, that's not what I have written down.
That's right. That's right, yeah.
Oh, that's weird.
2 electron volts over velocity.
What do you have written down?
That's
Exact Z squared over 8.
I have p squared over 2m.
Where's the square?
p squared. There's no mass.
I have a different solution written down than I did last time.
Where was slaughter?
Oh, because we don't know its velocity. That's what the problem was.
So what do you make velocity to?
Wrote this in with
Time out.
In a circle.
Okay, sorry, we do have to do a little erasing.
Harness the power directed to the center that you could technically move faster than speed.
You should, yeah, by all means, you should be using pencil. I wanted a different rearrangement of EK equals 1/2 mv squared. Because we don't have velocity, okay, what we actually have to do is multiply this by m over m. Okay, we're not changing the equation, multiplying it by 1. What that gives us is m squared v squared over 2m. M squared v squared is momentum squared.
so crazy.
I know.
When you're what?
Multiplied by 1.
Yeah.
Yeah.
So what you missed is the different rearrangement of, because we didn't have velocity in the equation, we had to use a different rearrangement of the kinetic energy formula. By multiplying by m over m, we're able to say that we've got p squared over 2m. Okay. So in this case, p is going to equal 2m ev all square rooted.
Alex fancy.
So what's your thing?
9.11 times 10 to the negative 31 is the mass. Okay, the mass of the electron is a given 9.11 times 10 to the negative 31 kilograms. Elementary charge 1.6 times 10 to the negative 19. The voltage is 1200 volts. Putting it all together, what do we get?
Josh?
3.4. 3.5 times 10.
No.
No.
1.87.
That's right.
Negative
20.
Right, we got to square root it.
Oh.
Screw.
It's 10 to the negative 23.
Yeah, 1.87 times 10 to the negative 23.
23, I got negative.
Rob, what's the unit on momentum?
Here. That newtons per kilogram per second.
Did you just make that up?
No.
Okay.
Because mass.
Yeah, it's mass times velocity. Kilogram meters per second.
What are you complicating?
That's okay.
we done?
No, we're not done. What are we at? What's the question asking for? Wavelength. So that was, I guess, step 1 and 2.
Right, we're on example 2.
Step 1, step 2.
Yeah.
Divided by Planck constant divided by that.
That's right. And now it's just wavelength equals Planck divided by momentum. I keep forgetting Planck's constant.
6.67. So 6.63.
6.67 or 3? 3. That's it. And we get a final answer of 3.35, 3.55. 3.55 times 10 to the negative 11.
I mean, technically it's just 3.5 because it's rounding becomes awkward when you have 4 or 5.
I use all the digits after the digit.
Because technically, overall, the next digit is less than 5, so you would round it down.
That's right. It doesn't matter.
Yeah.
What is the, okay, so is that a bigger or smaller wavelength than light, visible light?
That's bigger. No.
Wait, it was 10 to the negative 9.
Yeah, so it's smaller.
That's
Much
right.
smaller.
Remember, visible wavelength is in the hundreds of nanometers, which is 10 to the negative 7.
Oh, okay, so this is
So
much
electrons are like 1/10,000th that wavelength. So the bigger the particle, the smaller the de Broglie wavelength. And you get to the point where, I mean, the problem is that at a certain point above the size of small molecules, the de Broglie wavelength is bigger than the size of the molecule, or smaller than the size of the molecules. So if you're trying to use a double slit experiment to cause interference to measure the wavelength, well, you can't, because the molecules themselves don't fit through the double slit. So Josh, you're saying you can't do
For
a
now.
double slit.
You're just making bigger deficit.
But the separation of the slits versus their width has to be a certain ratio as well, and it doesn't work for big molecules.
Big molecules, Josh.
So is this the
Okay, you want some good practice? Do a unit analysis. Show me how that equals. Show me how this equals meters. Take 2 minutes right now and see if you can do that.
So, yeah, seconds cancel out. What?
Did you just say seconds cancel out when you have seconds to the power of -1?
Oh yeah,
Over seconds to the power of -1. Oh, yeah. Okay.
Okay, geez.
Oh.
Time.
No. Give us the answer.
Well, I gave you the answer that it works, but I want to show why it works. I'm serious, guys. Give it a try. You have to break down joules first.
Meters, meters, seconds. Oh, meters. But then you just get you can do like, you can break it out even further and break newtons down into meters per second squared.
There we go, I got it.
It is.
Newtons per meter second squared.
Newtons per meter second squared.